Salutations, mini mathematicians. We're going to be working on simplifying radicals today. This gets you set up for my favorite lesson of the year. Okay, so 6.1e, simplifying radicals. We're going to simplify the radical or the square root expressions completely, including variables, decimals, fractions, all without a calculator. Well, at least without the square root button of the calculator. So no square root button allowed today. If you have a basic calculator, obviously I'm using a scientific calculator. If you had a basic calculator, we can use it to divide by perfect squares, but that's about it. So you'll probably want to write the perfect squares at the top of your paper. 1 squared is 1, 2 squared is 4, so the next perfect square is 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196. So those are the perfect squares up to 14 squared. And those are the ones you'll probably want to start memorizing for the most success in this module. Okay, so I'm going to show you a few expressions that are already completely simplified. So we already are seeing these completely simplified. Square root of 8 is 2 root 2. Square root of 18 is 3 root 2. Root 32 is 4 root 2. So what do you notice here? Are there any observations you can make about the simplified square root? Something I notice is, well, first of all, obviously that's all 2 on the inside. The number left on the inside of the radical doesn't have any perfect square factors other than 1. So we know it's completely simplified. The other thing I notice is if I square the number on the outside and multiply it by the number on the inside, I get back to this original. So what I'm saying is if I have 2 squared times 2, that's 4 times 2, which is 8. And that's kind of the steps that we took. We took the square root of 8 and we broke it into its perfect square factors. So 4 times what? 2. And then 4 is 2 squared, and we know square roots and squaring are inverse operations. So we know they undo each other, so I can pull that 2 out, and there's 1, 2 left inside. The same thing, square root of 18, well, I can square that 3, so it goes back inside. And this is 9 times 2, which is 18. Okay. So again, you can see if I put that 4 back inside, I'd square it. And that's 16, which is a perfect square, which is 32. So note, if we are in completely simplest form, what we are looking for is number inside the square root or the radical has no perfect square factors other than 1. Excellent. Really nice job. Okay. So taking a look, the next thing we're going to be doing is we're going to look at simplifying. So there's 2 methods you can use to simplify. So we're going to talk about method 1, which is a factor tree. So on a factor tree, if we were thinking about square rooting, remember, square roots and squares are inverse operations, so we want to look for pairs. So you're going to pick pairs off your tree. Pick, and not the pears you eat, although delicious, but this is pears, P-A-I-R-S. Pick pairs off your tree. Okay, so method 1, what we have is we start with the square root of 40. And we think of what is a factor of the square root of 40. Well, one factor of the square root of 40, and it's also a perfect square, square root of 4 times square root of 10. Now from here, I'm going to leave this 4 here, and I'm going to see, oh, well, 10 is square root of 5 times square root of 2. So I'm going to keep going with this 4. And once I get to my roots, which are my prime factors, 2, 2, 5, 2, or root 2, root 2, root 5, root 2. So I know that the square root of 40 is equal to, and we're going to pick off pairs. So root 2 and root 2 here are a pair. I know you're like, what about that one? Yes, you could have paired these two together if you wanted to. They're also friends, but one of them's going to get left out. So this is going to be root 2 squared times 5 times 2. So because this 2 is getting squared, it can get pulled out. Since everything's being multiplied, that's why we can break them into their own radicals and square roots. And this is only true if everything is being multiplied. Remember that for the end of this lesson. Only true if everything's being multiplied. So you can think about this as the square root of 2 squared times the square root of 5 times 2. Square roots and squaring are inverse operations. So we have a 2 here and root 10, and that's our final answer. And again, you can always double check. 2 squared is 4, 4 times 10 is 40, and that's the original number we started with. Nice work, mini mathematicians. Okay, so the second method we're going to look at, method 2. Method 2 is the GPSF. You're like, what, Mrs. Barr? You totally made that up. Well, maybe I did, but it stands for the greatest perfect square factor. Nice. Cool. So greatest perfect square factor. So when we're looking at the greatest perfect square factor, just kind of like the greatest factor, right, of a number. We're thinking about the biggest number that goes into them, but we want to think about perfect squares. So these are the numbers we want to think about going into the number always, so we can break it up into a number being squared. Square roots and squares are inverse operations so that they would cancel out. Okay, so greatest perfect square factor, the GPSF. So again, we're going to do square root of 40. And I know the square root of 40 is the greatest perfect square that goes into 40 is 4. And if you weren't sure, you can just always start with your list and you can think, okay, 40 divided by, well, 25 doesn't work, right? Okay, 40 divided by, you can think about 9, that doesn't work. 40 divided by, well, 16, oops, 16, another perfect square. That doesn't work, but I know that 40 divided by 4 is 10. So this square root of 40 is equal to the square root of 4 times 10. And we know that the square root of 4 is 2 squared. And 10, we can't break it up into any other perfect square factors. Its greatest perfect square factor is 1, so I know it's already in the simplest form. Square roots and squares are inverse operations. So this is 2 square root 10. Not surprised we got the same answer. And you can use either of these methods. Obviously, the factor tree might take a little more space, so you might want to have a separate piece of paper to show some work. But sometimes for some of the numbers you're not as familiar with, it might help you, especially if you don't have a calculator handy. Okay, so the next set of directions is to simplify and show all your work. So if I look at number 3, doing this with a factor tree, instead of always writing these square roots, what I'm going to do is I'm going to say this breaks into, I'm just going to put a giant square root like around it, just so I don't have to keep writing that. I think of 1800, the biggest perfect square factor that goes into it. Oh, I think of 100. So 100 times 18, and I know 100 is 10 times 10. I'm going to stop here because this is a pair. Yes, I could break down into 5 and times 2 and 5 times 2 and make a pair of 5s and a pair of 2s. But remember our goal here. Our goal is to find pairs. So once you have a pair, you can stop over there on that branch for that root. Okay, but 18 I can keep going, and 18 I know is 9 times 2. 2 is a root, so I can stop there, and 9 is 3 and 3. Awesome. So again, what are we doing with our tree? Well, with our tree, we want to pick our pairs. So here's a pair, and here's a pair, but don't forget about this 2. That's why I like to put my little boats at the end of all my roots, so you don't lose any, right? They don't like run away. So we know that this is equal to the square root of 10 squared times 3 squared times 2. And what do you guys know? Square roots and squares are inverse operations. So what can we pull out? We can pull out the 10, we can pull out the 3, and anything that gets pulled out, of course, is still being multiplied, and the 2's left inside, and 10 times 3 is 30, so I have 30 square root, oops, that's a 2, 30 root 2, 30 square root 2. Awesome. So go ahead and pause the video and finish number 4, and we're going to go over the answer as soon as you are ready. Sorry guys, my 2 got really messed up. Okay, let's see how you did on number 4. So number 4, I'm going to show you the work both ways. So square root of 135, I broke up into 15 times 9, 15, 5, and 3, and 9 is 3 and 3. So I picked my pair of 3s, so 3 squared is underneath, and then the 5 times 3, and then I can pull out the 3 squared, because square roots and squares are inverse operations. And so it's 3 square root 15. If you're looking at this with perfect square factors, 135, I know 9 goes into that, 9 times 15, and then breaking up the 9 to 3 squared to pull out that, since square and square roots are inverse operations, and you get 3 square root 15. Nice, let's keep going. And again, you probably want to have your list of perfect squares somewhere near you so you can keep looking at it. It's really helpful. Okay, so what about variables? Ms. Barr, you said we're going to be simplifying variables to square roots. How do we do it? Well, it's pretty simple. So here we're going to simplify the square root of 3. So what we're going to do is we're always going to, if the exponent is odd, since square roots and squaring are inverse operations, we know that the square root of x squared is equal to x. Well, if you have something like x cubed, we're always going to rewrite it with an even power. So rewrite odd exponents as an even times a power of 1. Okay, so what does that mean? Well, 3 is odd. It's an odd number. So what we're going to do is we're going to rewrite it with an even, the biggest even exponent we can, which is x to the second. And we know that x to the second times x to the first, multiplying with the same base, you add your exponents. Oh my gosh, last module coming back at you, that these are equivalent expressions. Now we know that the square root of x squared times square root of x, square roots and squares are inverse operations. They cancel out. So this is equal to x square root x. So rewrite odd exponents as an even times a power of 1. I guess as an even exponent times a power of 1. So that's what I mean here. If we had an even exponent, such as the square root of y to the 8th, we're going to rewrite it to a power of 2 so that square roots and squaring are inverse operations and cancel out. So y to the 4th being squared, square rooted, power 4 times 2 is 8, which would be y to the 4th. You might notice a slick trick. So our slick trick is divide exponents by 2. Because, of course, since we're thinking about squaring, so we're taking half to use that power of power. So our slick trick is to divide exponents by 2 to pull out of the radical. Leave remainders inside. Leave remainders. Remainder. I guess there's only going to be one remainder, right? Because from an odd to an even, the difference is 1. Leave remainder inside. So using our slick trick, we can simplify something like the square root of w to the 11th power, because w to the 11th is w to the 10th times w to the 1st, all underneath that square root. Because w to the 10th is even, I can divide it by 2. Think about w to the 5th to the 2nd would be w to the 10th. Square roots and square inverse operations. So what I'm saying is this could be square root of w to the 5th to the 2nd times square root of w. So this is equal to w to the 5th square root w. Or you can take that shortcut from here. W to the 10th, half of it is 5, so w to the 5th when you pull it out of the radical, and that other w, that lonely w, just has to stay inside. Okay, so what we're going to do is I'm going to do 7 and 9 with you. So the first thing on number 7, I noticed it's the square root of 512x to the 4th power. So the first thing I'm going to do is I'm going to break it into 2 radicals. I'm going to break it into the radical of 512 times the radical of x to the 4th. And again, the reason I can do this is because everything is being multiplied. Okay, so from here, I'm thinking about 512, and I'm thinking about perfect squares. I know 25 is not going to work. Maybe 36. So 512 divided by 36. That didn't work. So maybe 512 divided by, I don't know, 16. Oh, 16 and 32. Nice. Okay, so I know that this is 512 is going to be 16 times 32. I'm going to close that. And square root of x to the 4th, even exponent divided by 2, pull it out, we get x squared. Okay, so from here, I could pull out this 16, but remember this 32 is also divisible by 16. So I'm going to say this is 16 times 16 times 2 times x squared. I could have also made a factor tree for 512. That probably would have been pretty helpful. That sometimes the factor tree, especially when you end up something like this, the factor tree kind of helps you see that sooner instead of doing extra work with perfect square factors. So here I can write this as the square root of 16 squared, square root of 2, all times x squared. This is going to be square roots and squares are inverse operations. 16 square root 2, all times x squared. And something that's important is numbers on the outside always get multiplied by numbers on the outside, and numbers on the inside of the radical only get multiplied by numbers on the inside. So to simplify this completely, this is 16x squared, square root 2. Final answer. Nice job. Okay, so let's take a look at 9. When I'm taking a look at 9, I want to remember what we talked about in our last lesson. When we looked at our last lesson, we had a talk about when you're multiplying the same decimal. I guess the lesson before this. So when we have this is, of course, I'm going to break it up, square root of 0.04, so 4/100ths times the square root of a to the 5th. And I think, okay, 4 is a perfect square. 2 times 2 is 4. And so since our product has 2 decimal places, I know that our factors, the numbers that multiply make the number, has 1 decimal place. So this is equal to 0.2 squared times, and rewrite a to the 5th as a to the 4th times a to the 1st, because we always rewrite odd exponents as an even times power of 1. And I know I'm taking the square root of a square, so they are inverse operations. And then a to the 4th, I can think about slicing that in half so it comes outside and it's an a squared. And what's left inside? Oh, just that square root a. So 2/10 a squared, square root a. Notice I don't have any parentheses, multiplication dots in my final answer. That is just how it is. Okay, so I'd love for you to pause the video, finish 6, 8, and 10. So I want you to do 6, 8, and look at 10, and we'll go over those answers in just a moment. Okay, let's take a look at number 6. So taking a look at number 6, your final answer should be y cubed square root y. And that's because we break up y to the 7th as y to the 6th times y all under the square root. To bring y to the 6th out, we divide by 2. or think about as y third to the second, and square roots and squaring are inverse operations. So you end up with y cubed square root y. Taking a look at 8 probably took you a little bit longer. Breaking this up, 1,728 times n to the 8th times t to the 9th. Square root of n to the 8th gets you n to the 4th. T to the 9th, we're going to break that up into the square root t to the 8th times t to the 1st. So that turns into t to the 4th times square root t. Well, 1,728, I know that 36 goes into it. It's 36 times 48. 36 is 6 squared. 48 is 16 times 3, and 16 is 4 squared. So I pulled out the 6, and I pulled out the 4, and the 3 is left inside. So then I just had to go and think about the 6, the 4, the n to the 4th, and the t to the 4th all on the outside. 6 times 4 is 24. And then this square root of 3 and square root of t are both on the inside here. So when I completely simplify that, I get 24 n to the 4th, t to the 4th, square root of 3t. Nice work. Okay. And again, your work might look slightly different than mine. I'm showing a little bit more work just in case people look at my answer key and need to know exactly what I did. But maybe you saw different factors, so it'll look different, but you'll end up with the same answer. Okay, so why is it important for us to assume that all variables represent positive real numbers? So we talked about this at the beginning of our module. You cannot take the square root of a negative number. It is not real. It's imaginary. And no number times itself is ever a negative number. And I want you to expand that, thinking that no number times itself an even number of times is a negative number. Because as we continue this module, we're going to look at not just square roots, but cube roots and fourth roots and fifth roots and sixth roots. And sometimes you can take the root of a negative number, but you can't take a square root, or in fact an even root or an even radical of a negative number, because no number times itself an even number of times is negative. So if you take a number and multiply itself by itself twice, it's going to end up being positive. If you take any number, multiply by itself 4 times, it's going to end up being positive. If you take any number, multiply by itself 6 times, it's going to end up being positive. Okay, so the next problem we're going to look at, when you have the square root of a fraction, that's going to be equal to the square root of the numerator over the square root of the denominator, and then you can simplify from there. So square root of 75 is square root of 25 times square root of 3. Square root of 4 is 2 squared, and square roots and squares are inverse operations. So from here, 25 is 5 squared, so they also cancel out. So we end up with 5 square root 3 all over 2. We always want to write this as one simplified ratio. So something special to note, and we're going to look into this more in detail in our next lesson, but if you have the square root of a number over the square root of a number, that's the square root of that whole fraction. And vice versa, if you have the square root of a fraction, that is the square root of the numerator over the square root of the denominator. So again, take a moment, write that down. Really important note for you. Okay, so let's take a look and practice our skills. So the next directions say simplify the following square roots. Assume all variables represent positive numbers, because remember, we cannot take the square root or an even root of a negative number. Okay, so 128, square root of 128, we can use a factor tree here or factor out our greatest perfect square factor, GPS of. So I'm going to use a factor tree here. So I'm going to say 128. I'm just going to draw a big square root symbol, and 128. 128. Well, I know it's even, then it's even again, so I know 4 will work. So let's see, 128 divided by 4, I get 32. And you guys are going to end up with 32 a lot, and I want you to break that habit of, oh my gosh, so break that habit of that. Whenever I see 32, I automatically usually think about 8 times 4. But what I want you to think about, because we're thinking about perfect squares, I want you to think about 32 as 16 times 2. So maybe put that up at the top of your paper, because it's going to come up a lot. This module, you're going to run as 32. And if you break it into 8 times 4, then you're going to have to break down 8 again into 2 times 4, and then you get that 4 times 4, which is 16. So make yourself a note and it'll help you throughout this module. 32 is 16 times 2. And then 16 we know is 4 and 4. So I'm going to stop at this 2. I'm going to stop at this pair of 4s. I'm going to break this 4 down again into 2 2s so that I can pick my pairs. Here's a pair and here's a pair. And don't forget about your buddy here. So we know that the square root of 128 is the square root of 2 squared times 4 squared times 2. And if you ever want to double check that you did it right, you could always check that. 4 times 16 times 2. Yep, 128, feeling good. So from here, what are we going to do? We're going to pull out the 2, we're going to pull out the 4. We're leaving the 2 inside. 2 times 4 is 8, so we have 8 square root 2. Box, circle, give your final answer a little bit of flair. Okay, let's take a look at 14. So when we take a look at 14, I notice I have this negative on the outside. So when you have this negative on the outside, that's exactly what it's doing. It's just hanging out. It's this -1 times the square root of 48. So again, I'm going to make a quick factor tree for 48. I really think that these sometimes, even though they take a little more space, can be the fastest way, because once I see 48 and I think of 4, and I can see, 12, and then you can think, 12 is also 4, so maybe 48 divided by 16. Okay, so I'm going to have 16 and 3. Oops, forgot my big radical. And 16 is 4 and 4. So then I can have my roots and then pick my pairs. So I have -1 times, and 48 is square root 4 squared times 3. Square roots and squares are inverse operations. So when you pull out the 4 squared, it becomes just 4. That 3 stays on the inside. So my final answer is -4 root 3. You can say -4 root 3, -4 radical 3, -4 square root 3. Lots of ways we can say these answers. Okay, so let's take a look at 15. Hey, this is that rule we were just talking about, where this is the square root of a fraction, so we can think about this as the square root of the numerator over the square root of the denominator. And maybe you notice, hey-oh, they're already perfect squares. 36 is 6 squared, and 144 is 12 squares, and square roots and squares are inverse operations. So we get 6 over 12. And of course, for all of these, always check at the end if your answer is completely simplified. Notice 6 goes into both of these, so we end up with our final answer of 1/2. Nice work. Okay, so you're going to finish 13, 16, 17, 18, and 19. You're going to finish this page. A hint for 17 is rewrite this decimal as a fraction. So this is 12 hundredths, the square root of 12 hundredths, so 12 over 100. Okay, and remember that rule that if there's the square root of a fraction, it's the square root of the numerator over the square root of the denominator. And what's awesome is 100 is a perfect square. Okay, good luck. You're going to do awesome. Okay, let's see how we did. Taking a look at 13, again, we are using that new rule of the square root of a fraction, the square root of the numerator over the square root of the denominator. Simplify, and you get 1/9. Good job there. Taking a look at 16, here again, very similar to 14 above, we have the square root of, we have -5 outside being multiplied by that square root. Here I decided to factor out my greatest perfect square. So 45 is 9 times 5. When I pull out that 9, it becomes a 3. So I have -5 times 3 on the outside, and just that 5's left inside. So -15 root 5, or -15 square root 5. 17, hopefully you took my hint and you rewrote this as a square root of 12 over 100, which is square root of 12 over the square root of 100. Square root of 100 we know is 10. 12 square root of 4 times square root of 3. Square root of 4 is 2 squared, so the 2 pulls out and the 3 stays on the inside. Notice 2 and 10, since these are both numbers on the outside, they can be simplified. So if you stopped at 2 root 3 over 10, Notice that that has to be root 3 over 5. So always, always check your answer to see if numbers on the outside can simplify together. Awesome. And then when we look at 18, taking a look at 18 here, I broke this up into square root of 16 times square root of a to the 5th. Square root of 16 is 4. A to the 5th we rewrite as a to the 4th times 1. A to the 4th, take half of it, and it's a squared on the outside. That a stays on the inside. So we have 4a squared, square root a. And the last problem that you had to do, square root of 50, x to the 11th, I broke up into square root of 50 times square root of x to the 11th. Square root of 50 is square root of 25 times square root of 2. 25 is our perfect square, so that becomes 5. 2 stays on the inside. Square root of x to the 11th, square root of x to the 10th times square root of x to the 1st. If you like drawing that exponent of 1 there, if that makes it easier, it makes it easier for me. Please do that. Help yourself out. Take half of the square root and pull it on out, and then multiply everything on the outside, multiply everything on the inside. So we have 5x to the 5th, square root of 2x. So you can kind of think about this as commutative property multiplication, moving them around. Nice. Again, numbers on the outside, numbers on the outside, numbers on the inside, numbers on the inside. Simplify, simplify, simplify that radical. Awesome. Okay, so we are jumping to our last page. You guys are doing a great job so far. Okay, so I'm going to help you out with the odds, and you're going to do the evens on your own. So 21, taking a look at 21, we have 5 on the outside, and we have the square root of 45 hundredths on the inside. Notice this is not a multiple of a perfect square. Like I can't, it's like 0.09, so I can say that's 0.3 squared. So I'm going to rewrite it as a fraction, and this is 45 hundredths, which is excellent because here it's going to be 5 over 1. So then it's square root of 45 over square root of 100. So this is 5 over 1, square root of 100 is 10, and 45 we know is 9 times 5. So from here we have 5 over 1 times square root of 9 is 3, so 3 root 5 all over 10. And you can start simplifying the numbers on the outside from here, or you can think 5 times 3 is 15, so you have 15 root 5 all over 10. A common mistake here is that people will want to simplify every single number, but remember it's only numbers on the outside with numbers on the outside. So 5 goes into 10 twice and into 15 3 times. And of course we want to write this as one ratio. So this is 3 square root 5 all over 2. Nice work, mini mathematicians. Okay, taking a look at our next one, we're going to break this into the square root of 120 times the square root of x squared times the square root of y to the 5th. So from here, square root of 120, we can start thinking of perfect squares that go into 120. I think about 120. Let's check 16. Oh, that doesn't work. Well, 120 divided by 4. Even numbers, typically that works. So 4 times 30. Square root of x squared we know is x because they're inverse operations. And we're going to rewrite y to the 5th as square root of y to the 4th times y to the 1st. Okay, so from here, we know that square root of 4 is 2, so I can pull that out. Leave the square root of 30 on the inside. I have the square root of x, and then, sorry, just x now. I misspoke. And then the square root of y to the 4th, take half of that, pull it out, y to the 2nd, and that y other one just stays on the inside. From here, square root of 30 does not have any perfect square factor, so it just has to stay on the inside. Remember, numbers on the outside times numbers on the outside, numbers on the inside times numbers on the inside. Simplify, simplify, simplify that radical. Dun, 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 dun. Final answer, 2xy to the 2nd power, square root 30y. Bam, bam, bam. Okay. Okay, let's take a look at this next one. This is a pretty cool one because we can use our knowledge of multiplying decimals again. So we have 1, 2, 3, 4 decimal places in our final factor, which means we have 2 decimal places in our factor. So we have, again, like I said, 4 decimal places in our final product. I think I said it wrong a second ago. So 4 decimal places in our final product, which means we have 2 in our factor because it's the same number being multiplied. So taking a look here, we have the square root of 0.0081 times square root of a to the 6. So this is the square root of 0.1234 decimal places, so 2. Square root of 81 is 9. And this is, remember, we can cut this in half. And we can think about these square roots and squares canceling out to get our final answer of 9/100 a to the 3rd power. Groovy. Okay, so this next one is important. So remember, we can only break up the radical if everything is being multiplied. But here we do not have multiplication. Boo! Well, if you don't have it, you make it, right? We make things happen here. So rewrite with multiplication. Rewrite with multiplication. And hopefully we can rewrite multiplication, hoping with a perfect square. Woo, perfect square. That is just, the stars are aligning. So if we take a look at 200n minus 100, is there a perfect square that goes into both of those terms? Indeed, there is. 100 is a perfect square that goes into both of them. So 100 times what is 200n? 2n. 100 times what is negative 100? Negative 1. So from here, now that we have multiplication, we can break up the square root with just what's being multiplied. So this is square root of 100 times the square root of 2n minus 1. Square root of 100, that's 10. You can't touch this. It doesn't matter if it's a 4n in there or a 16n. If there's a minus a number and we can't rewrite it with multiplication, it just has to stay like it is. So this is 10 square root of all of 2n minus 1. Awesome. So remember that when we are working with 26, you can't break them into different radicals until everything is with multiplication. So just rewrite it with it. You want it, you make it happen. Okay, so you're going to finish this page and we're going to go over our answers in just a moment. Okay, so taking a look at number 20, final answer is 18n to the 4th square root 2. That 3 is on the outside just waiting to get multiplied. 72, 9 times 8, square root of 9 is 3, so that comes out. 8 is 4 times 2, so maybe from the beginning you saw maybe a bigger number that went into it. Nice, good job, you guys. Square root of 4 is 2, so that comes out. Square root of n to the 8th is n to the 4th, so that also comes out. So we have 9 times 2, which is 18, n to the 4th, and square root of 2 just stays on the inside. Okay, on 22, we have the square root of 0.0025. Notice because this is 4 decimal places, our square root of it has 2 decimal places. So 25 perfect square root of 25 is 5, so 0.05. A to the 3rd, square root of a to the 3rd, we break up into the square root of a squared times a. Always rewrite it with that even, you guys. Always rewrite it with that even power times the power of 1. Square root of a squared is a. That other a stays inside. Square root of b just hangs out the whole time, you guys. So this is 0.05a times the square root of ab, or just square root of ab. You don't have to say times. Notice we don't have any parentheses or multiplication dots there. A lot of talking today. You're like, what else is new, Mrs. Barr? You're always talking to us. It's true. I like you guys. Okay, so next problem. Square root of x to the 7th, square root of y to the 10th. Again, our slick trick could come in handy here. I'm showing extra work just in case people were looking at the work to figure out what I did. Rewrite x to square root x to the 7th as square root x to the 6th times square root of x to the 1. Square root of x to the 6th is x to the 3rd. Take half of that exponent. square root of y to the 10th, take half of that exponent, it's already even, y to the 5th, x to the 3rd, y to the 5th, square root x. Again, we're writing these expressions in simplest form, alphabetical order, numbers outside the radical in front, numbers inside the radical on the inside. If there was a coefficient, of course, that would go in front. Okay, and the last one, remember, you can only break up the radicals if being multiplied, so rewrite with multiplication. 4x plus 16, the perfect square goes into that is 4. So this is 4 times x is 4x, and 4 times 4 is 16. So I can break it up into square root of 4 and the square root of x plus 4. Square root of 4 is 2. I can't touch this 4, you guys, that's inside here because it's being added to the x. Order of operations, we would have to do x plus 4 first before we take that square root. Awesome. Really nice job, mini mathematicians. I hope you enjoyed simplifying radicals. And again, getting ready. We need this skill for the rest of this module. Your teacher next year is expecting you to know how to do this. And it's getting ready for one of my most favorite lessons. See you next time. Stay psyched, do your best, be nice to everyone, and make it the best day ever.